Hello, I'd like to welcome you to today's Makino Experience Center presentation. My name is Bill Howard. I'm the product line manager for vertical machining centers here at Makino. In today's presentation, we're going to talk about heat. Can't stand the heat. It's an overall overview of machine thermal considerations. Little housekeeping item here. You should be able to see in the upper right-hand corner of your screen a little chat and Q&A. As we're talking today, if you have questions, you can go in and enter those, and hopefully we'll have time at the end of the presentation that will address those questions. So don't forget about the chat box there and your ability to submit questions and answers. I'm sorry, questions that hopefully I'll get time to answer. I'm coming to you today from one of two experience centers here at Makino in Mason, Ohio. That's the facility on the far right of the screen. I'm in EC1. EC2 is down the hall. We also have at our Auburn Hills facility in Auburn Hills, Michigan, 2 additional EC centers. Now, while we're talking about EC centers, I'd like to encourage you that if you have a project you'd like to talk about, either a machine or a part or a process or automation, we have the ability here with these EC centers to host a private, very directed, confidential session specifically about your needs, whether it be a machine, processing, tooling, automation. So just keep that in the back of your mind that we have the capability with these EC centers to do that kind of focused presentations. We'll get on to today's EC event. And as I said, it's Can't Stand the Heat. It's an overview of thermodynamic issues, thermal considerations with a machine tool. Start with just a little kind of overview. It's probably old hat for a lot of you folks, but just to give you an idea what we're chasing here, there's a straight pin. So that's what a straight pin would look like. This is a human hair, or maybe beard hair in my case, but you're looking at about 100 micron. Well, this is 1 thou, or 25.4 micron. Okay, we can go down and pollen that floats around in the air, about 20 micron. Well, a human red blood cell, about 8 micron. Then we can get down to 1/10,000th of an inch, which is 2.54 micron. And then we get down to 1 micron, which is 40 millionths of an inch. So we're taking an inch and cutting it into, 40 million. It's 1/1,000,000th of a meter, or 1/1000th of a millimeter, or 1 micron is also 1,000 nanometers. So just to kind of give you some perspective of where we're headed with this. What's the impact of heat? Well, number one, I'm sure everybody realizes and recognizes this, but every material, you'll see there aluminum and bronze, cast iron, every material has what's called a C factor. It's the coefficient of linear expansion, and it's in inches per inch per degree Fahrenheit. So you'll see here, aluminum, 12.6. Look down here at steel, mild steel, cast iron, 5.9. So you'll notice that aluminum grows a lot more than either cast iron or steel. Well, let's just get an idea. What's a typical tolerance? Well, what about 2 thou, which would be 50 micron, or 3 thou, which would be 75 micron? Well, keep in mind now, we just showed you, human hair is about 100 micron. So that gives you an idea of the tolerances you're chasing with a machine tool. You can see a human hair is already significantly bigger than the tolerances we're looking at. Now let's take, in the back of our mind, picture a mid-sized vertical machining center, say a 40 by 20 platform. And let's say we want to put a feature in, and it happens to be 10 inches long, which should be fine on a 40 by 20 machine, either way. Or let's take a look at 15 inches. Well, a thermal error budget would go in and take a look, and my father used to say, well, it's pretty close, we're only off by a hair. So that gives you an idea of what that statement meant. Here's a plot, and this is aluminum here in the gold, and that is cast iron and steel. If you go in and look at, and this is at the 2 thou tolerance, or 50 microns, so that's what that vertical, 7.5 degrees temperature is going to consume half of your tolerance. So if I simply have a 7.5 degree change, I'm going to take up half of my total 50 micron tolerance just in thermals. Now in steel or cast iron, because the coefficient is about half, it's about 16 degrees. Now let's go out and look at the bigger tolerance. Let's just go out here and say we're going to look at the 15-inch long feature. And again, there's your tolerance, 75 micron, about 8 degrees. Whereas cast iron and steel, again, 16 degrees. And you'll notice with cast iron and steel, we have a shot of getting it in. Whereas if you look at the aluminum, there's the potential that it's going to grow enough that we're going to have a lot of points that are going to fall outside of the allowable tolerance. So basically, what is the impact of heat? Consider error mapping, and that's kind of what we just did. If you go in there, machine error, well, that's all machine errors. That's geometric, positioning accuracy, repeatability, squareness, straightness, parallelism. So, and thermal. And we just saw that we've used up half of the allowable error for those kind of tolerances, 50 micron, 2 thou, 3 thou. We've used up half of it in thermal. Forget about the rest of the machine error. Then you've got initial part error. Well, what do you mean by that? Well, castings could be off, the locators could be misaligned, so there's things there. There's work holding error. There's tooling error and processing error. And then there's checking errors, how you check the part. So if you add all these together, our initial thermal example used up half of the total allowable tolerance. So the bottom line, I would say yes, it's pretty important to pay attention to heat and the impact of heat upon your manufacturing operations. Now, what's your shop environment? Is your shop temperature controlled? Let's take a look at this picture. Uh-oh, what do you see sitting there right beside that open door? Right there where the arrow is. Well, lo and behold, that's a machine tool. Now, given that guy standing there looks like he's shivering and he's got a sweatshirt on, what do you think the temperature impact upon that machine sitting there right by the door is when that door is open and people are moving things in and out? So you need to be aware of that. Let's take a machine tool. Here's the basic castings. This happens to be an F5 vertical machining center. And this is the thermal profile. This is looking at the air around that machine. And consequently, the further away from the wall, obviously the more stable the environment, the blues. The greens, obviously, there's a lot of change. And the other one is vertically. Again, as you go down along the floor, about mid-height, it's relatively stable. But as you get next to walls or next to doors, or as you go up in height, the temperature in your shop changes. That's what that shows. Well, again, let's take a look at the vertical machining center. And as you can see over there on the left-hand side of the screen, that happens to be a shop, and in a particular case, the ceiling height is 33 feet tall. And what this is a plot of various different points on the machine and the temperature change. And you can see it's all, the temperature is warming. So the bottom line here in this example, in a 33-foot tall factory, you could see from the floor to the ceiling potential of 14.4 degrees, over 14 degrees in temperature change. And the thing is, it's going to be stratified. It's going to be cooler along the floor, and as you go up, it's going to get warmer, and you notice it's warmest along the roof of the building. So, shop environment. Impact on structure. Well, let's take a column, and here on the left side's a traditional vertical column, and you'll notice there's no temperature gradient figured into this. On the right-hand side, we've figured in a temperature gradient, and we've colored that in red. As the column goes up, the temperature is going to get warmer and warmer as it goes up, so the casting is going to grow. And so consequently, you have a delta L there, a change in the length, if you will. Actually, it's the width, front to back, but of that column. There it is. Now, what does that do to your machine tool? Well, traditional machine tools should look like that. There's the carrier, the spindle, the carrier on the front of the column. Actually, what happens when that column starts to grow, the spindle and the carrier are no longer straight and square, as you can see here. So consequently, what happens? Well, there's going to be an impact, and a lot of people call it point. What that means is as that changes, the spindle starts to point either in the Y positive, Y negative, it can point in X, and actually can grow up and down in Z. So consequently, as you can see, the change in that geometry can impact not only your X-axis, but it can impact your Y-axis and your Z-axis as well. And you'll notice they're going all different directions. X is going positive, Y and Z are going negative. So your point in space is a conglomeration of all of those. Now, the other thing, if you think about it, major axes, X, Y, Z, there's a squareness factor. Well, that's what I'm showing here. What happens when you get thermal growth and you have the column growing and therefore the spindle no longer perpendicular to the bed? Well, obviously that angle changes from 90 degrees to some other angle. So consequently, your relationships between, in this case, your Z-axis and your Y-axis changes dramatically. This is an example of a thermal image of the Z-axis, and you can see again, obviously very hot down by the spindle, but you can see it pointing also if you look at it. So that's an effect of thermals, not only of your environment, but also of the spindle. Is heat important? Well, let's just talk about, for each axis of a machine tool, you have 7 degrees of freedom. If you think about it, you have horizontal straightness. So is it straight horizontally? You have vertical straightness. Is it straight vertically? Then you have squareness. And you can see Z to X, Z to Y, Y to Z. So that's your major coordinate system. In addition, if you start moving, you have roll. The next thing you have is pitch. Is it pitching up, pitching down? And last but not least is yaw. Is it going this way? So, and then obviously the one everybody's familiar with, positioning, accuracy, and repeatability. You roll them into one. So if you count those up, there's 7 degrees of freedom there. So consequently, on a 3-axis machine, 3 times 7, there's 21 degrees of freedom. So there's 21 potential things that are moving around here And thermals impact all of those. So we've got to control those thermals. Why? Well, think about it. How do you program a part? Whether it be contouring or point to point, drilling holes. How do you program that part? Well, typically XYZ. Well, that refers back to a machine tool and a coordinate system. So we have XYZ points, or XYZ point to XYZ point to XYZ point in the case of contouring. What happens, and that's how you literally replicate your part on the machine tool, is by definition of the axes and the travels and the motion and the points to point. What happens when you lose that relationship? Well, all of that goes away. So the final part you machine is dependent upon all those geometries, those 21 degrees of freedom, thermals, and once you lose that, you've lost the relationship of those major coordinate systems. So that's an impact on your part. Are there solutions? Well, absolutely. Casting design, that happens to be an F9. It's a Makino machine, but you'll notice large heavy-duty castings. What's that do for you? It gives you a very long thermal time constant. It's going to take a long time to change the temperature of those castings. It also provides you good stiffness and rigidity, which ensures those geometries. The other thing, it's symmetrical if you look. So if you do have thermal changes in your shop, the machine's going to grow symmetrically and maintain those 21 degrees of freedom. Another thing that, again, a Makino-esque solution, the castings are blue, so you can see every now and then blue sticking through. Well, just like your home, if your home's cold or you spend a lot of money heating your home, what do? Well, you put insulation around the house. That prevents the heat from migrating in the summer, and it prevents the cold from migrating in the winter. Well, that's exactly what we've done here. We've put insulation, that gray material, insulation over the castings, and that's going to maintain the temperature of the castings for a longer thermal time constant and keep cold air or hot air from migrating into the castings. So layers of thermal protection. Another thing, if you think about floor to ceiling, the colder air is along the floor, the hotter air. So on most machining centers, the air comes in at the bottom, migrates up through the work zone, and goes out through the top. Well, can you fix that? Yes, you can. Again, a Makino S, this happens to be a V33i, but you'll notice the skirt goes all the way down to the floor. It seals against the floor. That's to prevent cold air from coming in along and rolling up along the castings. You'll also notice we put a top, what we call a thermal guard, over the top of the machine. So not only do we prevent air from coming in from the bottom and working up, we prevent air from migrating up through the work zone. Limits airflow or migration from the cooler to the hotter. The other solution is grab control of that environment. Take control of your manufacturing shop, your environment. Control temperature, floor to ceiling, wall to wall. Humidity. Limit exposure to outside air, whether it be through doors, a dock, whatever. You saw that machine sitting right by the doors. Can you imagine, I don't know how many times a day those doors open and close, or the difference in the environment in the shop versus outside? But you can bet it's not having a positive impact on the accuracies you're trying to machine on that machine. And this is one that we've learned, sun. In a lot of manufacturing shops have great big glass windows, and the idea there is to make it pleasant, a lot of sun coming in and light. Well, that sun can also fall upon the machine tools, and that can be a temperature gradient and can cause thermal growth of the machine. So keep that in mind. Other machine factors to consider. Well, I think everybody would have picked this one, and they typically do, the spindle that generates heat, obviously. The thing about the spindle, and you'll notice the faster you go, the more heat you're going to generate. Where are the heat sources on a spindle? Well, number one, and being a vertical guy, I call this the lower bearings. On a horizontal, it would be the front bearings. Same thing here, it'd be the upper bearings on a vertical or the rear on a horizontal. So the bearing areas and then the integral motor. So you'll notice how red hot those areas are, and it looks like the hottest area is that integral motor. Well, here's kind of this monitored about 11 different temperature sources. And the key thing to notice here is the differential between the motor and the housing, the cast iron. You're looking at 7 degrees C, or about 44 degrees Fahrenheit, and that's if you do nothing. Okay, so that, and you'll notice there's varying different temperatures depending on which component or element you're measuring. The other thing about it, and this is a issue or problem too, is time lag. Heat takes time to migrate through. So consequently, you'll notice that it takes time. There's a time lag between the RPM you're running, the heat generation, and the change or error in z-axis. So that we got to be cognizant and aware of. Another thing, when you're designing a machine, the bearing has, and I've highlighted it in red here, a typical design limit for the bearings, and that's what's shown in red. And you'll see the theoretical capacity and all that. Well, most folks, when they design a machine tool, have a factor of safety, that's the green here, and you'll notice where that's at. But as people want to push higher and higher RPM, the competition, oh, they've got a 12,000, oh, they got a 14, oh, they got a 15, oh, they got a 20. As people push RPM, one of the tricks that they're doing here is they'll add that little area there to move the RPM out, the purple. And what they'll do in order to stay in the safety range is they'll reduce the preload. So now at the high end, you'll notice that we're still under the load limit by spindle design, the blue line there. But at the beginning, you'll notice there in the orange or the pink that we've had to back off on the preload. Well, what's that mean? It means that low RPMs, that spindle is going to be loose and shaky. There's going to be different cutting conditions there than there are as that spindle grows and takes up that preload lack. So you have different cutting conditions depending on how long you've been cutting and the RPM you're cutting at. Well, another thing is, understand that lubrication is critical. There are 12 reasons why bearings fail. First is lubrication, and it's estimated at up to 80%. 80%, that's 8 and 10. 80% of all bearing failures are a lack of lubrication. Contamination, that's also related to lubrication. Improper mounting, that's a design issue, and I would encourage you to work with machine tool builders that have a reputation for good, solid spindle design. Same thing with misalignments. False Sprinelling, that's related to lubrication. What false Sprinelling is there's a lack of lubrication. So as the balls are rolling, there's a load, and that ball either Brinells or Brinells the spindle. And what caused that? Well, there's not enough lubrication there. Corrosion, another. You get areas where there's not getting lubrication, that exposes the components to the air, and you could end up with corrosion. Electrical damage, we'll talk about that here in a minute. Fatigue, again, that's wrong design bearing if they're fatiguing. Overheat, again, lubrication. Excessive loads, that's polite for crash. Improper storage and handling, that's a handling issue, or fit. And again, that goes back to design. 5 of the 12 reasons, or 42%, are related to lubrication. Well, how do you attack that issue? Well, again, lubrication is critical. Bearings need lubrication. But the key thing you got to be careful, if you just dump, like here, lubrication on there, you're going to end up with too much lubrication. You're going to end up with viscous shearing, trying to move that oil around, and it's going to generate more heat, which is exactly the opposite of what you want to do. If you have too little, then you've got, number one, ineffective heat removal, or absorption, and you expose yourself to what we talked about earlier on corrosion. And the other thing is it's got to be the right kind. If you get the wrong viscosity, thickness, I mean, you can see there different oils and the heat profile of those oils. So if you wanted the ideal thing might be to get a real thick, heavy duty because that will coat everything and soak up the heat. Yes, but you're going to generate a lot of heat trying to move that around. So wrong viscosity can be an issue and problem as well. How do you solve that? Well, again, kind of a Makino-esque solution. We've went to an air and oil bearing lubrication. Basically what you have is you have a volume of air metered and a volume of oil, a metered volume of oil. You bring those together at a mixing valve so you can control the air and the oil. What you're trying to do is get an outlet that's a continuous flow of little what's called droplets, very, very fine droplets. So you got the oil suspended in air. So now you have an ability to move that lubrication wherever you need it without having to contact the parts, and you can get flow into areas where you couldn't plumb it up and get it in there anyhow. The idea is to have that congeal on the rolling elements, the moving elements, the hot elements, and then soak up the heat, lubricate it, and then take it out. What would that look like? Well, this is a schematic, but this is the air oil being applied to the bearing. The key, this is typically what, if you went down and physically looked at the components on the machine. The other thing about this, you have a slightly positive air pressure. So that prevents contaminants from getting into the spindle, the bearings. And if you think about that air, it flows over those surfaces where the oil is congealed. So if there's excess oil, the wetting parameters will keep the oil there you need. If there's excess oil, that air will move it away. And it moves it away. There's not a big fog or mist or whatever, so it's environmentally friendly. Here again, what are the benefits? Well, very, very small amounts of oil, so there's no viscous shearing and no heat generation. Lower friction, again, because there's no viscous shearing and heat generation, and you're getting the oil, the micro droplets, to all the areas that need lubricated. You end up with less wear, which means you increase your bearing life. The bearing temperatures as a result of this methodology remain relatively constant. Keep in mind you got the oil and you have the air. Only fresh oil is brought into the system, so you don't have a deterioration or a contamination potential with the oil. You can have up to 70% reduced oil consumption. Less oil changes, reduced maintenance, lower operating costs. So let's go back to that spindle again. We knew where the heat was being generated. So how do we attack that? Well, number one, let's do air oil to the bearings. You'll notice there's two sets of bearings at the low end of the spindles. So you air oil to those, and then air oil to the high end, to the bearings at the top or back of the spindle. So air oil to the bearings. And then the other big heat area was where? In around the armature of the motor. So we want to put a jacket so that we've got air oil to the bearings, but we want to control the temperature of the casting around those bearings. So that's what we're doing there. And we want to get the heat from the motor and remove it. So we have a jacket around where the integral motor's at to remove the heat. What's the result? Again, this is a test that we typically run on our product and competitive product. It's called a pyramid test. And we literally cut this. You cut various different depths, as you can see, and you go off and you cycle between those various different depths. And what you're looking for is the result like this. That's our machine and a competitor machine. And what you'll find here, our machine was a 15-minute saturation time. The competitor was 45 minutes. You'll also find that our machine saturated with about 8 microns The competitive machine saturated at about 40 microns. So we have 1/3 of the stabilization time, so you can get up and get running, and we have 20% of the thermal growth. Again, let's go back. Remember at the very beginning we were chasing a 2 thou or a 3 thou tolerance. Well, if you've got 40 micron, you know, the 2 thou was 50 micron. We've taken up 4/5, 80% of the tolerance just in thermal growth. So it's critical that you look at machine tools that have a methodology for controlling the thermals in the spindle. What would a typical ideal conditions be? Well, I'd like a quick saturation, minimal time to stabilize. Once it gets there, I'd like to run at full speed and have very minimal growth. And I'd like the overall to be 7 micron or less. And that's especially important if you're doing die mold, where you're doing matching and blending and things like that. So that's what I'd like to see. Other machine factors to consider, let's move on. Servo motors. Obviously you have servo motors on XYZ. You have ball screws, XYZ. You've got ball nut. You have bearings. You also have a tool changer motor. Let's talk about the coolant system. You have all kinds of coolant, which means you have pumps. You have a lift-up chip conveyor motor. If it happens to be a drum-type filtration, you have a motor for the drum. So there's all kinds of heat being generated there. If you think about it for a second, all of the heat from your cutting is going into the coolant. And that goes down across the machine and back into the chip and coolant tank, and therefore is on your machine. So it adds heat to the coolant and system. And it can impact not only your machining, but your machining operations. As an example, this is a coolant temperature controller, you can see here. And what that allows us to do is it's a Freon type chiller, takes heat out of the coolant rather than maintaining it, and obviously it's going to keep building all day. There's all kinds of pumps and support items, motors, pumps, hydraulics, all of that in the machine tool. What I've done here is took a typical PS105, a Makino machine, and I've listed all of the motors, the kilowatts, the horsepower, the number, and come up with a total. And then knowing the conversion from horsepower to BTU per hour, I've come up with the fact that for every hour this machine runs, it's generating 190,000 BTU. So, what does that mean? Is that significant? Well, unfortunately, BTU, there's not a direct conversion. BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. So what I had to do was go in and convert, and it's based upon the mass of air, the specific heat of air, and the delta temperature I want to see, delta change. So how much heat does it take to raise the temperature? So I did some kind of calculations, which just show you, give you an idea of what I had to go through to get there. But I finally get there. So there's a heat factor. So now what I can do is go over and take that machine, the PS105, and I'm going to build a little room around it. 12 by 12 by 9 feet tall, which happens to be 1,300 cubic feet. Now, how much heat's generated? Well, if I take that factor times 190,000 BTUs, that says I can change for 190 degrees for every cubic foot of air I have. Well, that's not really fair, because if you think about the machine, the spindle motor's not running all the time, the servo motors aren't running all the time, the coolant pumps may not be running all the time, the hydraulics, so that's kind of an overstatement. Let's get more realistic like I said, that assumes 100% of the time. Let's use a 50% factor. Let's get rid of that 190 and let's take it down to 95. All right, well then it comes up 95, 96 degrees per cubic foot. Well, again, remember that PS 105 is about 1,300 cubic feet. So with that factor, if I had that machine in that room, 12 by 12 by 9, and didn't do something to basically ameliorate, get rid of all that heat, I would raise the heat by 14 degrees Fahrenheit for every hour that I ran the machine. So over an 8-hour shift, that's 112 degrees. So that also speaks to not having the machine back in a corner or boxed in or in a little small room, having a lot more area. But ultimately, it says you really need to take control of the environment that machine is in. Is your shop temperature controlled? And again, keep in mind, there's 112 degrees over an 8-hour shift. We're chasing 50 to 75 microns here. Another big area is ball screws. Every machine's got XYZ ball screws. Here's a heat profile, and you can see the ball screw is getting hot. Not only is it's hotter at the bearing end, and even hotter at the motor and the casting. And all that heat's migrating into the machine. Well, here's an example where the top there, we went 2 hours and 30 minutes, 4 hours and 30 minutes, 6 hours and 30 minutes. So 6.5 hours. And you can see everything's still relatively low heat. Here's a competitive machine, same time frame. Look, 2.5 hours, 4 hours and 30 minutes, 6 hours and 30. Look at the glowing yellows and reds. Not only is it in the ball screw, but it's moving up into the casting, so it's heating up. Now, how do you take care of that? Well, that's a typical ball screw. Most people talk about pre-tensioning the ball screw. Well, the middle one there, we've pre-tensioned the ball screw, okay? And notice what happens. We've pre-tensioned the ball screw, and now what happens, because of that delta there, the whole ball screw, as you're going one direction and reverse the other, the whole ball screw can flip back and forth by that little amount there shown in red. What does that do to contouring capability? What's that do to your positioning accuracies and repeatability? Now, here we've done the same thing. We've pre-tensioned the ball screw prior to running it. And again, the whole ball screw is not going to shift back and forth, but we've not accounted for the heat. And so consequently, it's going to continue as the ball screw heats up, it's going to grow out the end. As you can see there, that little bit of red at the very end. Now, what I've got here is looking at a bed and the ball screw, and we've got sensors, and what we've come to find out in this particular case, if you look at the casting and you look at the ball screw, there's about a 3 degree C or a 37 degree Fahrenheit difference. Now, if I go back and use that coefficient of expansion, 37 degrees times, let's say, a 40 by 20 machine, a 20-inch long ball screw, that's 118 microns of growth. We're, again, shooting for 50 to 75. So, another thing, the higher the rapids, and that's what this is, more and more rapid, well, more and more thermal growth. The longer the cycle time you run. So as you can see here, 50 minutes, 30 minutes, 20 minutes. So the longer the cycle time, the more growth. The bigger the machine. And that's what this is showing. Travel. So the bigger the machine, the more thermal growth. So obviously this can impact you in a number of ways. How do you resolve that? Well, again, this is a Makino-esque, but we've gone to core-cooled ball screws. What we do is we bring lubricant in through the down screw end, go around the bearings, come out of the bearings into the ball screw, up, come out of that, go around the bearings, and then out. And we control that with a oilmatic unit to maintain temperature. So we can control the thermal growth, provides temperature stability, minimizes displacement or growth, higher accuracies. What are the advantages? Well, shorter warm-up cycles. Number 2, lower stabilization temperature. What's it mean? Well, lower stabilization means less thermal growth, but it also means reduced operating temperatures and longer. Anytime you can reduce the temperature of components, it means they're going to run longer, so longer component life. And again, this is a Makino-esque, but what we've shown here is we have the spindle, so we have all of that jacket and everything around the spindle. Then we go through X, Y, and Z servo ball screws from support end to motor end. We recollect all that and go through an oilmatic unit. Now, it doesn't make sense, and there's amazing how many folks do not use an oilmatic unit, but you got to take the heat out. There's no sense just recirculating the heat. So what we're doing here, we put a thermocouple in the bed of the machine, we measure the temperature of the bed, and we maintain all of this with the oilmatic to within plus or minus 2 degrees F. So we've created an ambient manufacturing zone where all the elements of the machine are related to each other temperature-wise. Here's what it looks like. Here's the down screw end. You can see oil coming in around the bearings, through the ball screw, up through the ball screw, around the bearings, out, and then back to the oilmatic. Okay, so let's, as a wrap up here, let's try and put all of this together. And this is a little animation, but what we've got is a bed. And this happens to be the D200Z. You'll notice we're measuring the temperature of the bed. There's a thermocouple in there. There's the oilmatic unit. We're sending lubricant to the spindle and the jacket around it, to the ball screws, from down screw to up screw. And in this case, there happens to be a tilt trunnion table with DD motors, so to those, we're recollecting all that back to the oilmatic unit. We're then looking at the temperature of the bed, and we're adjusting these flows to be within 2 degrees C. So again, in essence, what we've done is we've taken all the machining elements of the machine and we've tied them to the bed temperature so that we can enhance the thermal performance of the machine. That's what I have for today. At this point in time, we'll break for questions and answers.
As we've been talking, there were a couple questions that were previously submitted, so I'll go ahead and start addressing those. However, you will notice on your screen there on the upper right, the Q&A button is still there. So feel free if while we're talking, something comes to mind, just enter it in and send it in, and we'll try to address it. One of the questions that was previously submitted was you used the word oilmatic, and I admit I used it a lot in the presentation, but you never really tell us what an oilmatic is. Well, what in again Makino-esque vernacular, what that is a freon or a chiller. It's a heat exchanger. If you think about it, we're collecting all this heat. If we don't get it out of the system, we're just going to constantly build heat upon heat, and we're not going to get anywhere. So what this Freon chiller is basically it will heat exchange. It will take the heat out and therefore help us to maintain temperature. There was also a question previously submitted about, do you have a reference, or are you keeping it to ambient air, or what are you doing? Well, in that last little present video there, we actually, if you think about the machine, all of the components on the machine are related to each other. The bed, the ball screw, the spindle, all of that. We want to maintain all the temperatures relative to the bed temperature, because then in an essence, what we've done is created an ambient manufacturing zone where the bed of the machine, all the components, the ball screw, the spindle, the bearings, all of them are at the same temperature. So that ambient manufacturing zone is going to enhance the accuracies that we can maintain on the machine. There was another previously submitted question about is can it be done where rather than having multiple oilmatics and multiple flows, can one flow service multiple components? And again, in that last little composite video that we showed on a lot of our machines, we actually showed the one we showed you there was from a D200Z, but the oilmatic and the flow is going to the spindle, around the spindle and the jacket, through the core of the spindle to maintain the spindle temperature. Then it's going through the ball, basically the bearing packages and the ball screws, core cooled ball screws, and out around the motor area. And then also in that particular case, it showed a DD motors around the tilt and rotary table. So yes, it's possible. Now, the key thing here is you obviously, again, we go back to Oilmatic, that's the heat exchanger. You have to size those circuits and you have to size that Oilmatic unit so that it can take out all of the heat if you're serving multiple componentry there. So I notice, number one, there's no more questions have come in. Oh, there is one. I can't see it. Oh, I'm in the wrong place. That's why. Do you monitor coolant temperature? Yes, we do monitor coolant. I'm sorry, I had my screen on the wrong. We monitor the coolant temperature. Matter of fact, in the presentation there, I showed where we had put an Oilmatic unit on the coolant. So if you think about all the heat that's generated cutting the workpiece typically flows into the coolant. As that coolant goes back into the coolant tank, unless we have a way to take that heat out of the coolant, again, it's going to constantly build and build and build to where over time you're going to see an increase in the coolant temperature. So we can put a thermocouple on the coolant. We can monitor and actually monitor that relative to the temperature of the bed. So if we need, we can add an optional chiller unit on the coolant so that now not only are all the machine elements relative to the temperature of the bed, we can maintain the coolant relative to the bed as well. I see we're running a little long on time. Before we go away, I'd like to remind you, if you've signed up for this, you should be receiving an email follow-up. So you'll be able to, again, take another look at this. If you other folks that you want to share this with, in a couple days, it'll actually be posted to our archive. It'll be at www.makino.com. So at that point in time, you could send it to other folks in your organization and use it for education or use within your organization. So I'd like to thank you on behalf of myself and the folks here at Makino for joining us today, and thank you very much.